energy, mostly in terms of, how fast it's zooming around.
Yeah, like simple kinetic energy.
But what if that's just one piece of a much bigger, maybe stranger puzzle? What if a particle holds just immense energy even when it's perfectly still?
Well, that's exactly the focus of the material you sent over. It's a really thorough analysis. It unpacks the total energy of a particle. And yeah, it reveals it's this complex composite, definitely not just about speed.
Right. And our goal for this deep dive is to be your guides, sort of, through that analysis. We're going to pull out the really crucial insights, show you how energy manifests in ways you might not expect, and we're drawing exclusively from the source material you shared.
Think of us as your shortcut, yeah, to grasping the fascinating, multifaceted nature of a particle's energy.
It's about moving beyond that sort of classical intuition, isn't it? Seeing how energy is tied to intrinsic properties, fundamental interaction.
Absolutely. It gets pretty deep.
Okay. So based on your material, where does this whole exploration start? What's the most fundamental bit?
It really starts with rest mass energy. EMCE.
The classic, the world's most famous equation. But what does it actually tell us about a particle's energy when it's, not even moving?
It reveals something pretty profound. Mass itself is a form of energy. It's this inherent energy content a particle has just because it has mass.
Regardless of motion.
Or position.
Exactly. It's the baseline energy, just by existing.
And the numbers the material gives for this are, well, they're kind of staggering, even for tiny particles. An electron, it says, has a rest energy of about half a mega-electron volt, 0.511 MeV.
Right, 0.511 MeV. And a proton, well, that's almost 1,000 MeV, around 938.
Wow.
What really stands out there is just how much potential energy is locked away, even in these minuscule bits of matter.
It's incredible. All that energy in something so small. And the material points out this isn't just, theoretical energy. It can be unleashed.
Yeah, the example given is particle-antiparticle annihilation, where the mass just gets converted entirely into energy, into photons.
Exactly. So mass isn't just inertia. It's literally a reservoir of energy.
Okay, so that's the energy it has just for being. What happens when we add motion? That brings in kinetic energy, yeah?
It does, and this is where things really diverge depending on how fast the particle's going. Your source highlights this really clearly.
So at everyday speeds, it's the kinetic energy we kind of learned in school, half mV squared.
Pretty much, yeah. But the analysis really digs into what happens when a particle gets close to the speed of light. That's where relativistic effects kick in.
Ah, right. That's where that gamma factor comes in, the Lorentz factor.
Exactly, gamma wave. The total energy becomes Gumpsche.
And the kinetic energy is that total minus the rest energy. So
yeah.
Guess one MC free.
You got it. And here's where it gets really interesting. This is a key aha moment from the source material. As a massive particle gets closer and closer to light speed, it just shoots towards infinity.
Infinity, which means its kinetic energy and, well, its total energy also heads towards infinity.
Precisely. And the material explains the huge consequence. You just can't provide infinite energy. It's impossible.
That's why nothing with mass can ever actually reach the speed of light. You just can't pump enough energy into it.
Exactly. It's a fundamental limit right there in the energy equation.
Wow. Okay, so energy from existing mass, energy from moving, kinetic. What about energy tied to where a particle is? Position.
Right, that's potential energy. It's the energy a particle has because of its position within some kind of force field.
Like gravity. Holding a ball up high. Or for charged particles, maybe.
Exactly that. The source mentions gravitational potential energy, the familiar m-pi from basic physics.
Right.
But what's really key in particle physics is electromagnetic potential energy, like an electron's energy, because of where it is relative to a nucleus in an atom.
Okay. So a system's total energy often includes that potential part plus the kinetic.
Yep. Kinetic plus potential is a common way to look at the total energy of a system.
And the source made this really interesting point about bound systems, like that electron stuck in an atom.
Ah, yes. In systems where particles are bound together, could be an electron in an atom or quarks in a proton, the total energy is often negative.
Negative energy, how does that work?
Well, if you connect it to the bigger picture, a negative total energy basically signifies stability. It means you actually have to add energy to the system to pull it apart, to overcome that binding force and free the particle.
Ah, okay. So it takes energy input to break them up. It's like they want to stay together.
Exactly. It's energetically favorable for them to be bound.
That makes sense. Okay, now, your source material goes into something maybe a bit less intuitive. How does a particle's electric charge itself contribute energy?
Right. So a charged particle creates an electric field around it, yeah. That field stretches out, and the field itself contains energy.
Okay.
Classically, there was this idea, sort of, that the energy stored in this field actually contributed to the particle's mass. They sometimes called it electromagnetic mass.
But the analysis points out a big problem classical physics hit there, didn't it?
Oh, yeah, a huge one. If you treat a charged particle like a perfect point, with zero size.
Which is how we often think of fundamental particles.
Right. Then the energy stored in its electric field, because the field gets infinitely strong right at the point, calculates out to be infinite.
Infinite energy. That feels
Yeah.
impossible. A breakdown, right?
Totally. It's a clear sign that classical theory just can't handle particles at that fundamental level. So the big question is, how does modern physics deal with this?
Does it?
It does. The source explains that quantum field theory, QFT, it resolves this. It uses a technique called renormalization.
Renormalization.
Right.
Sounds technical. What's the gist of it, according to the material? How does it fix the infinity problem?
Okay, the key idea, basically, is that the energy of the electric field isn't some extra thing you add onto the particle. It's inherently tangled up with the particle itself.
So it's not separate.
No. The mass and energy that we actually measure for a particle in experiments, that observed value already includes a contribution from its own field energy. It's baked in from the start, not added on later.
Okay, so the energy of its own field is just part of the particle's identity, part of its measured mass and energy. Got it. What about quantum spin? The source mentions this too. Does that mean particles are actually spinning, like tiny tops? Rotational energy.
That's a really common misconception, and the source is quite clear on this. Quantum spin is, well, it's fundamental. It's purely quantum mechanical. It is not the particle physically rotating.
Okay, not actual spinning.
Right. And crucially, for a free particle just moving along, this intrinsic spin doesn't add any classical kinetic energy.
So if it's not kinetic energy, how does spin contribute to the total energy? The material must explain that.
It does, and it's through interactions. Spin matters when the particle interacts with fields or other properties. The source details a couple of key ways this happens.
Like spin-orbit interaction, so on?
Exactly that one. So imagine an electron orbiting a nucleus in an atom. It's moving, right? From the electron's perspective, that motion creates a magnetic field. The nucleus seems to be circling it. The electron's intrinsic spin then interacts with this magnetic field it experiences.
Okay.
This spin-orbit coupling causes tiny shifts in the electron's energy level, really small changes.
And that's observable.
Yep. It shows up as what's called fine structure. If you look very, very closely at the light emitted by atoms, their spectra, tiny splits in the energy line.
Wow, subtle. Okay, what's the other interaction?
Interaction with external magnetic fields. Because a particle has spin, it also has a magnetic moment. Essentially, it acts like a tiny compass needle, a tiny magnet.
Right.
So if you put that particle in an external magnetic field, like from a big magnet, its energy will depend on how its spin, its little internal magnet, is oriented relative to that external field. Pointing with the field is lower energy than pointing against it.
And the source points out that this effect, this energy difference based on spin orientation in a field, is the fundamental principle behind technologies like NMR, nuclear magnetic resonance.
Exactly. NMR and also MRI in medicine, medical resonance imaging. It directly uses the energy associated with nuclear spin in a magnetic field.
That's a really concrete, practical application of this, well, pretty abstract quantum spin energy concept.
It really shows how these fundamental quantum properties have real-world, tangible effects. It's not just theory.
Okay, right. We focused a lot on fundamental particles, like electrons. But what about composite particles, things made of other things, like protons and neutrons, the stuff that makes up, well, us and everything around us? Your source reveals something truly astonishing here.
Yeah, this was one of the points in the material that really made me pause. Protons and neutrons, they aren't fundamental, they're composites. They're made of quarks, held together by gluons mediating the strong nuclear force.
Right. Quarks and gluons. And the striking fact, the really mind-blowing part the source highlights, is that the actual rest mass of the quarks inside a proton, it's only about 1% of the proton's total mass.
It's incredible, isn't it? Just
So,
1%.
Where on earth does the other 99% of the mass come from? That seems crazy.
It comes from the energy of the inner workings, basically. The source explains it beautifully. The vast majority of a proton's mass, its mass energy, comes from two main things happening inside.
Okay.
First, the intense kinetic energy of the quarks and gluons. They're not just sitting there, they're zipping around inside the proton at speeds incredibly close to the speed of light. Relativistically, the material calls this a kind of vibrational energy.
So internal motion energy, what's the second thing?
The second is the immense potential energy stored in the strong force field that binds those quarks and gluons together, the energy in the glue.
So wait, let me get it straight. The mass of this microphone, the desk, me, which is mostly protons and neutrons, that mass is not primarily the mass of the little quarks inside. It's mostly the energy of their frantic motion and the energy holding them together.
That's exactly what the source material indicates. If we connect this to the bigger picture, this internal dynamic energy, kinetic, and potential is the dominant source of the mass of virtually all the ordinary matter we see and interact with.
That just fundamentally changes how you think about mass itself. It's mostly energy.
It really does. It's one of the most profound insights from modern physics, I think.
Wow. Okay. Bringing it all together then, the source culminates by talking about the most complete picture we have. Quantum field theory. QFT.
Right. QFT provides this really powerful, unifying perspective on all of this.
How does it view particles and energy?
Well, instead of tiny billiard balls, QFT sees fundamental particles as localized excitations. Think of them like vibrations or ripples in fundamental fields that permeate all of space-time.
Fields for everything.
Yeah, there's an electron field, a photon field, that's the electromagnetic field, quark fields, gluon fields. So an electron isn't just a point particle, it's an excitation, a ripple in the electron field. A photon is an excitation in the electromagnetic field.
So a particle's energy in this QFT view is essentially the energy contained in that specific ripple or excitation of the field.
Precisely. It's the energy of the excited state of the field and the mass of the particle. That corresponds to the minimum energy required to even create that excitation in the first place, the energy cost of making that ripple.
And what's really neat here, connecting back, is how this perspective kind of gathers up all the pieces we talked about. The energy of a particle's own field, like the electron's electric field.
In QFT, that's not separate. It's naturally part of the energy of the excited electron field itself. It's all integrated.
And interactions.
Interactions between particles are seen as exchanges of these field excitations. It just provides this overarching, consistent framework. It links mass, energy, fields, and forces together.
Okay, so pulling back from this deep dive into your source material, the big takeaway is that a particle's total energy is, well, it's far from simple. It's this incredibly rich, complex mixture.
Absolutely. You've got energy just from its existence, its rest mass.
Then energy from its motion, its kinetic energy, with those wild relativistic effects near light speed.
Okay. Then energy from its position in force fields, potential energy.
Plus the energy tied up in its own associated field, especially for charged particles, which QFT tells us is part of its measured being.
And energy from how its intrinsic quantum spin interacts with things.
And then for composite particles, like our protons and neutrons, the absolute stunner. The bulk of their mass, like 99%, comes from the energetic chaos inside.
Yeah, the furious kinetic energy of quarks and gluons and the potential energy of the strong force binding them.
And QFT kind of elegantly wraps it all up, seeing particles as excitations in fundamental fields, where mass and energy are just deeply intertwined aspects of how these fields behave.
Exactly. Energy isn't just one thing. It's this incredibly versatile concept, fundamental to everything, from a particle just sitting there to its most complex internal dynamics and how it interacts with the universe around it.
So what does this all mean for you listening? Maybe think about this, drawing right from the source material we explored. The fact that the mass of your hand, the air you're breathing, the earth under your feet, it's made mostly of protons and neutrons, right? And nearly all 99% of their mass isn't from the stuff they're made of, the quarks. It's from the energy of that frantic dance happening inside them, and the energy holding it all together.
It's quite a thought.
It really is. Energy isn't just something that makes things move or happen. In a very real, fundamental sense, derived right from this physics. Energy is actually what things are, something that you want.